Finally, we're going to talk about the laws that govern interactions between circuit elements. There are two of these, Kirchoff's current law and Kirchoff's voltage law. This video covers Kirchoff's current law. Kirchoff's current law, or KCL for short, is very simple. The sum of all the currents entering a node or leaving a node is zero. Really, all this is telling us is that the total charge at a node can't change. So, any charge entering a node has to be balanced by an equal charge leaving the node. This means that another way of stating KCL is that the sum of the currents entering a node is equal to the sum of the currents leaving the node. In order to apply KCL, we need to be able to identify a node. One definition is that a node is where two or more circuit elements are connected. A better definition of a node is that a node's a region in the circuit within which the voltage is all the same. Perfect conductors, by definition, don't cause a voltage drop when current flows through them, which means that a node will generally contain perfect conductors. However, a simple node will not contain any circuit element that causes a voltage change. Later on, I'll talk about what are called supernodes, which can contain circuit elements. But for now, we'll assume that only perfect conductors belong inside a node. Now let's take a look at a quick example to see what I'm talking about in the context of a circuit schematic. In this circuit schematic, lines represent perfect conductors. They have no voltage drop across them. The dots simply indicate interconnections between perfect conductors. These three elements come together at a single point. That would be considered a node. This entire section here is a node interconnecting these four elements. This perfect conductor inside here doesn't have a voltage difference, so this is all at a unique voltage. This point and this point each interconnect two elements. Those would both be nodes, and this entire bottom section here contains only perfect conductors, so that is also all one node. The signs on the currents are super important to applying KCL. So let's summarize the process. Before you apply KCL, you need to indicate what your assumed positive current directions are. These assumed directions are what you use to decide whether a current is entering or leaving a node. When you apply KCL, you also need to decide whether you want currents entering the node to be assumed to be positive or currents leaving the node to be assumed positive. Either choice is okay. But once you choose a sign convention for a particular node, you need to stick with it. Then use your assumed current direction and your assumption as to whether positive currents correspond to entering or leaving the node when you write KCL. If you're consistent about how you define your current directions and how you treat the signs on the current, KCL will make sure that everything works out, and the signs on your resulting currents will correctly identify the actual current direction. Don't waste your time trying to decide which directions the currents at a node are actually in when you define them. Just choose a reference direction and stick with it. You do not need to keep the same kind of sign convention for all the nodes in the circuit, so you can make different assumptions for each time you apply KCL to a node. However, for any one node, you do need to be consistent. Now let's do a couple more examples. Since the sum of the currents in KCL is an algebraic sum, that means that we have to account for the sign of the currents when we add them up. The sign of the current is associated with the assumed current direction rather than the actual current direction. Let's look at a quick example to see what this means. We have a circuit node here with n currents, all of which are defined as positive leaving the node. The currents are I1, I2, and so on up to I sub n. So, if we assume positive currents are leaving the node, my assumption of positive current direction matches the directions of all these currents, so they will all be positive contributions. So I1 plus I2 plus a bunch of other terms plus I sub n sums to 0. We can choose a different sign convention. Say we assume that positive currents are entering. Now my positive current direction, for example, for I1 is this direction. Switching the direction of the arrow changes the sign on the current. So this is negative I1 entering. The same switching on signs is associated with all the other terms. So negative I1 minus I2 minus I3 minus I sub n is equal to 0. These are the same equation. If I multiply this equation by negative 1, I get this equation. Also notice that from these equations, at least one of the currents will need to be negative. This simply means that at least one of the currents will be entering the node, which is consistent with our alternate statement of KCL. The currents entering the node have to be balanced by the currents leaving the node. I'm going to do KCL at this node to determine this current I. We're given three other currents with their assumed positive direction and a numerical value. So negative 1 amp here simply means that 1 amp is going in the opposite direction. So if I assume positive currents leaving, four amps is entering, I have to change its sign. So minus 4 amps. This current is leaving, so it's positive, but its value is a negative 1 amp. This one's leaving, so I add 2 amps. And I is leaving, so I add I. And that sums to 0. So negative 5 plus 2 is negative 3. Taking that over to the other side, I is equal to 3 amps. I should get the same result by assuming positive currents entering. So 4 amps is entering, that's a positive current. This current is leaving, so it's negative, but its value is negative 1 amp. This current is leaving, so that's a negative 2 amps. I is leaving, so that's negative. That sums to 0, and this will still give me I is equal to 3 amps. That's really all there is to KCL. It's very simple to apply as long as you keep track of your assumptions. Whatever you do, don't try to predict the current directions before you do your analysis. Just make your assumptions and stick to them. The next video covers Kirchoff's voltage law.